Hello everyone. Today we are going to finish the story of Extrema. In our first video on Extrema, we saw there are two types of Extrema. One is local Extrema and the other one is global Extrema. And we also saw that it's not that hard to figure out those global Extrema of a continuous function on a closed bounded interval. The harder question was to figure out the local Extrema of a function. And we made some progress on that direction. We talked about critical numbers. We saw that if a function has a local maximum or a local minimum, then at a point, then at those points the first derivative vanishes or first derivative does not exist. And that became the definition of critical numbers. And also from the graph of a function, we saw what happens when it has a local maximum or a local minimum. But the problem was we don't know the graph of a function beforehand. Graphing a function is a very challenging thing, right? So we wanted to come up with some smarter ways to get those information from the rule of the function. And for that reason, we needed to talk about mean value theorem. And in the last few videos, we talked about mean value theorem, which is a very important topic on its own. But in the last video, which was on monotone functions, we saw what happens if the derivative of a function is strictly bigger than 0. I mean, strictly positive. In short, when a function has a strictly positive derivative in an interval, in some open interval, then it is strictly increasing. And that's what we were looking for, okay? So now that we know that fact, we can actually connect all our dots and finish the story of Extrema, okay? So let's start with a simple graph, which we already have seen many times, especially in the first video on Extrema. And then from there, I will just review some of the basic things we talked earlier. And then we'll talk about the first derivative test. Okay, this is the test that we have been looking for so long. And after that, I will use that first derivative test to find local extrema of two different functions. Okay, I'm going to solve two examples, and that will be the end of this video. Okay, so let's start. This is Extrema part 2. So let's start with a graph. Suppose we have a graph of a function like this. How should I start? Let's say this is point A, and we want to start from there. Let's say the graph goes like this. And let's make it a little bit bigger, like this, and it comes down here, and from there it becomes like that. Okay. All right, so we have a function f that is continuous in this closed bounded interval a to b. Okay, now let's say this point is c, this point is d, and let's say this one is E. Okay, now let's write down the local extrema. By the way, in this video I'm not going to talk about global extrema at all. If you want to know about global extrema, please watch the first video on Extrema. We finished the story of global extrema there. Okay, so this video is completely focused on local extrema. All right, so here what is the local maximum? It's the local, it's the highest value, right? So if you look at this point C and take any interval containing C, then you will see f of C is the largest value in that tiny interval, right? So f of C is definitely a local maximum. Does it have any other local maximum? Yes, f of E, right? Once again, take some small interval containing that point, and the value which is the largest among all the outputs coming from this interval is a local maximum there, right? So which is f of E. So these are local maximum. What about local minimum? f of d, right? Notice f of b, that's not a local minimum, because when you talk about local maximum or local minimum, we need to have an interval that is completely inside the domain. Okay, and here if I want to fit an interval, say like this, but there is another part, right? But that part will go outside of the domain. The domain of this function is this interval a to b. Okay, so we cannot fit any interval there, and therefore f of b cannot be a local minimum. And same here for f of a. Okay, there is no interval that fits there, right? These points will get outside of the domain, so that's hopeless. Okay, so we don't do that. Okay, so these are local minimum. Just to complete the story, what are the global extrema? So global maximum is the highest output, right, for all these inputs coming from this interval, which is f of c. Okay, and oh god, so which one is the largest, f of a, smallest, f of a or f of b? Let me just make this a little bit, yeah, upper. Okay, all right, now there is no confusion. So global minimum is going to be f of b. That's the smallest value. This is f of b. Okay, and now notice we're not going to talk about global max and global min, so we'll completely forget about this part. We'll be focusing on this part, local max, local min. Okay, now notice here at this point c, the tangent has horizontal slope. I mean the tangent is horizontal, so it has slope 0. That's what I wanted to say. So f prime of c equals to 0, right? And also at d, you have a horizontal tangent, so that means f prime of d is also 0, right? But at e, there is no unique tangent. There are two different tangent directions, right? In other words, f prime of e does not exist. Okay, so that became our definition of critical number, right? So a number, so definition, this is from last time. Let f be a function and let x equal to c be a number in its domain. Okay, in the domain of f. Okay, so last time we solved problems, we figured out the critical numbers of a given function, and once you do that, you always need to be careful about this thing. This number has to come from the domain. Okay, all right, so then x equal to c is a critical number of f or for f, doesn't matter, of f if, so one of the two things happen: if f prime of c equals to 0, or f prime of c does not exist, right? And last time we also talked about Fermat's theorem. From that theorem we saw that if a function has a local extrema at a point, and if the function is differentiable at that point, then f prime of that point is 0. Okay, but also we saw other examples like absolute value of x. It has a local minimum at the origin, right? But it's not differentiable there. So we have that other condition that f prime of c does not exist. So these two conditions actually define what a critical number is. Okay, but so from last time we had this fact: if f has a critical, if f has a local extremum at x equal to c, then x equal to c is a critical number. Of f. Okay, I need this picture for a while, so I'm going to erase this board now. Critical number of f. Okay, and then we had a cautionary remark. This is a very important cautionary remark. Caution. X equal to c is a critical number let me write in a different way. Not all critical numbers give a local extrema. Okay, so you have the function f, you can take its derivative and then set it equal to 0, or from that derivative function you can see where it does not exist, and if you solve that equation f prime of x equal to 0 and see where it does not exist, you get the critical numbers, right? And if the function has a local extrema at anywhere, that will be in one of those critical numbers. But you need to remember this fact, not all critical numbers will give you a local extrema. Okay, and the reason why I kept this graph for a while, notice this part of the graph, kind of like this. Okay, so let's call this point P, and at P, if you draw a tangent, that also becomes horizontal, right? So here f prime of P also equals to 0. But notice f of P is neither a local maximum nor a local minimum, right? Because if you take any interval containing P, you see the values, the inputs which are coming from the right of P, they will produce higher outputs. So definitely f of P is not the largest value in that interval, right? And if you look at, so f of P is not a local maximum. And now let's focus on the inputs which are coming from the left of P. And notice those outputs, corresponding outputs, are less than f of P. That means f of P is not even the smallest one. So it is neither the largest one nor the smallest one. And so it's neither a local max nor a local min. So it's not a local extrema, okay? And also notice we have another point here. Let's call this Q. Notice here f prime of Q does not exist, right? Because you have two different tangent directions. In other words, this is a corner. That is also a corner, okay? So an extension of this picture, notice in the picture above, x equal to, so let me list the critical numbers. P is a critical number because derivative vanishes. C is a critical number, D is a critical number. E and Q, they are also critical numbers because derivative does not exist at those 2 points, okay? In the picture above, x equals to P, C, D, E, and Q are critical numbers. Critical numbers, okay? But f of P and f of Q are not local extrema. Okay? Alright, so you have done all these parts. Little bit of brush up on the definition of extrema. But the thing is, suppose you have a critical number. How do you know whether that gives you a local maximum or a local minimum? Right? Or maybe neither one. So we need some kind of test. Okay? And this picture actually captures all this information that we need to know. Notice here f of c is a local max, and if you look on the left side of this function, what happens is the function is increasing, right? By increasing, I mean take any 2 points, then the bigger input will give you the bigger output. That's what happens, okay? So since I have so many things written here, I will use this symbol, this arrow up, okay? So that will mean it's increasing. And notice on the right side of C, it is what? Decreasing, right? So arrow down, okay? Arrow up means increasing, arrow down means decreasing, okay? So if a function has a local maximum at a point, then on the left side of that point, the function increases, and on the right side of that point, the function decreases, okay? And the same happens here. So look at here, on the left side of E, the function is increasing, right? And after E, it is decreasing, okay? And whenever you have a local minimum, then what happens on the left side, oh God, this picture is so dense now. Okay, on the left side, oh, actually we have that information, we don't need to draw this. On the left side, it is decreasing, right? See, it is decreasing on the left side. And on the right side of D, it is increasing, right? Okay, so if you have a local maximum at a point, then on the left side of that point, the function increases, and on the right side of that point, the function decreases. And if you have a local minimum at a point, then on the left it decreases, and on the right it increases. That's the algorithm we need, okay? All right, and be careful about these 2 points, f of p and f of q. Notice on the left side, it is increasing, and also on the right side, okay? So that pattern doesn't change. And look at f of q. On the left, it is decreasing, and after q, it is also decreasing, okay? So if it is decreasing and decreasing, nothing happens. Or if it increases and increases, nothing happens, okay? But if it goes from increasing to decreasing or decreasing to increasing, then something interesting happens. So that's the first derivative test. I'm going to write it down, and after that we will apply this test to 2 different functions to find their local extrema, okay? All right. So first derivative test. So let f be a function and x equal to c be a critical number of f, okay? Let f be differentiable in an interval containing c except possibly at x equals to c, okay? Yeah, this is the funny part. In the textbook of Stewart, he has started saying the function is continuous. He didn't mention about differentiability, but when he mentioned about the tests, he mentioned about f prime. So it's kind of implicit that you are assuming the function is differentiable, okay? Now what I am writing here is this. We are talking about local extrema at point C, right? So this is a critical number, right? X is a critical number. Then 2 things can happen. Either derivative is 0. So whenever we say f prime of c is 0, that means f prime of c, first of all, it exists, okay? And the other thing is f prime of c may not exist, okay? So 2 things can happen. So it is possible that my function is not differentiable at c. So that's why we said that f is differentiable on this interval a to b, let f be differentiable in an interval containing c, okay, except possibly at c. If it's not differentiable at c, that's not a problem. Okay? Actually, we just need this interval and that interval. That's the content. Okay? All right. So I'm going to erase this from this test. Then we have this following criteria for local maximum and local minimum. So number one is this. If f prime increases, if f prime is positive, right? Is positive on the left of x equal to c and negative on the right of x equal to c, then what happens? So this is the moment where we are using that mean value theorem conclusion. If f prime of x is positive on the left side, then by the second proposition we proved in monotone function lecture, then this function is strictly increasing on the left side, right? And since f prime is negative on the right side on this interval, then again by that same proposition the function is strictly decreasing on the right side, and therefore f of c is a local maximum. Okay, then f of c is a local maximum. Okay, that is number one, and we'll write the same thing for the local minimum. Okay, so if f prime is negative on the left of x equals to c and positive, so I will keep this picture for a few more minutes, so I'm going to use this. Positive on the right of x equals to c, then notice, look at this point D. On the left side f prime is negative, that's why the function is strictly decreasing. On the right side f prime is positive, that's why the function is strictly increasing, right? So it's from decreasing to increasing. So at D it has a local minimum, right? Then f of D is a local minimum. Okay? Does it make sense? We have a very geometric interpretation of this thing, and then we can characterize those things in terms of derivative. That's the beauty of this problem. Okay? And the third part is this. If f prime is positive or negative, let me put this in the parentheses, okay, or negative on both sides of x equals to c, then f of c is neither a local maximum nor a local minimum. Okay, and for that let's just focus here at this point P. On the left side of P, f prime is positive, so it's strictly increasing, and on the right side of p it's also positive, so it is also strictly increasing, right? So then f of p is neither the highest nor the lowest, so it's neither local max nor local min. Similarly, at f of q, on the left side it is decreasing, so f prime is strictly negative, and on the right side f prime is also strictly negative, so it's also decreasing. So from decreasing to decreasing, that means f of q is neither the largest one nor the smallest one, so it's neither local max nor local min. Okay, that's the first derivative test. Okay, and every time you want to calculate local max or local min, if you forget the first derivative test, just draw a picture like this. This alone will tell you where to look and what to do. Okay, all right, now we are going to take this information and apply on two different functions. Okay, and that will be the end of this lecture. All right, so now I'm going to erase this picture finally. Okay, so example, for each of the following functions, find its local extrema. And the first one we are going to do is this: f of x equals to x times absolute value of x squared minus 12. That's our first function. Okay. Now if you look at the first derivative test, that gives you some algorithm. So first you need to find the derivative. Okay, and from there you need to find the critical numbers, and then you need to find the intervals on which your derivative is positive or negative, and that's it. Okay, so step 1 solution. Step 1, so let me give it a name, find f prime of x. Okay, that's a step 1, but to get f prime of x, actually for this problem it will be better if we simplify this function a little bit. Sorry, this function is not as nice as a polynomial function, so it will be better if we simplify this thing a little bit. Okay, step 0, simplify f. Okay. So when I say simplify, what do I mean? I mean we need to remove the absolute value. Absolute value functions are piecewise defined functions. That's it. You have a polynomial inside this absolute value, so once you remove the absolute value, it will become a polynomial, and it will be a very nice function at the end. Although you'll have several different polynomials because it's a piecewise defined function. Okay, but that's not a problem. So where should I start? Notice okay, so that's what we need to deal first. Absolute value of x squared minus 12, right? How does it look? X squared minus 12. Forget about absolute value. It's a parabola, right? Okay. And it opens upward. So it's a parabola like this. So this is x squared minus 12, right? And why does it hit 0? Here and there, right? And if you set x squared minus 12 equal to 0, you get x squared equals to 12. So x is square root of 12, right? So it's 2 times the square root of 3. So plus and minus, negative 2 square root of 3 and positive 2 square root of 3. Okay. So this guy is negative 2 square root of 3. That guy is 2 square root of 3. Okay. So if our x is between negative 2 square root of 3 to positive 2 square root of 3, then x squared minus 12 is negative. Otherwise, it is positive, right? Notice x squared minus 12 is less or equal to 0 if x is between negative 2 square root of 3 and positive 2 square root of 3. Okay, hence we can write this function as this. Hence absolute value of x squared minus 12, that guy is what? If x is less than negative 2 root 3, then this function is already positive. So absolute value does nothing to it. Okay, whenever the input inside absolute value is positive, absolute value just leave it as it is. So if x is less than or equal to negative 2 root 3, then this is just x squared minus 12. Okay, and this is negative x squared minus 12 if x is between negative 2 root 3 and positive 2 root 3, and this is x squared minus 12 if x is bigger or equal to 2 root 3. Okay, so we have just written absolute value of x squared minus 12 as piecewise defined function. That's it. All right. Now, what is our function? Our function is x times this guy. Okay. Therefore, f of x is going to be x times this, those three pieces. Okay. Therefore, f of x, which is x times absolute value of x squared minus 12, that guy is, first of all, this is x times this part, right? So this is x cubed minus 12x if x is less or equal to negative 2 square root of 3. And this is negative times x cubed minus 12x if x is between negative 2 square root of 3 and positive 2 square root of 3. Okay. And finally, this is the same thing, x cubed minus 12x if x is bigger or equal to 2 square root of 3. So that's my function f. Okay. So that was a step 0. We just simplified this function. Just high school algebra, or middle school algebra. Anyway, so now notice this function is given by 3 different polynomials and cubic polynomials. So they are very simple to differentiate. We are going to do that. But notice since it is given by 3 different polynomials, it will have 3 different formulas for derivative, but it will have something else. And what is that? Notice this is the graph of x squared minus 12, right? If I want to graph its absolute value, then what happens? This part will remain the same. This part will remain the same. Okay. And this negative part will become positive, right? Because we are multiplying that by a negative sign. Absolute value makes everything positive, right? So it will go like this. Okay. So this blue one, that is x absolute value of x squared minus 12. And notice this function has 2 corners, right? And that means this function is not differentiable at negative 2 square root of 3 and positive 2 square root of 3. Okay. Now our original function f is that function times x, but x is really good. It's just a polynomial. So the product will also not be differentiable at negative 2 square root of 3 and positive 2 square root of 3. And they are 2 critical numbers. That's the beauty of this problem. Okay. This problem kind of captures everything that you need. Okay. All right. So this is a step 1 now. Find the derivative. Okay. So then f prime of x is going to be what? Maybe I'll write it here because I have a long curly bracket. Okay, hopefully this will be fine. So if x is less than negative 2 root 3, then the derivative of that is 3x squared minus 12, right? And we can factor out 3 from those two terms. So this is 3 times x squared minus 4, okay? If x is less than, notice right now we are having strict inequality. We are not including negative 2 root 3 because at negative 2 root 3 f prime does not exist. And in fact that's the thing you need to write in the next line, okay? So d and e if x equals to negative 2 root 3, okay? This is one of the corner points. All right, and then from negative 2 root 3 to positive 2 root 3, this is given by the derivative of this function. Again, this is negative times 3x squared minus 12, so you can factor out that 3, so this is negative 3 times x squared minus 4. If x is strictly between negative 2 root 3 and positive 2 root 3, okay? And once again, we hit that number 2 square root of 3, right? And that is one of the points where we have a corner. So f prime of x does not exist if x equals to 2 square root of 3. Okay. And finally, we have the same polynomial on top. So this is 3 times x squared minus 4 if x is bigger than 2 root 3. So that is step 1 to get the derivative of the function. Okay. And what is step 2? Find the critical numbers, right? So critical numbers, let me remind you, are those numbers where f prime of x is either 0 or does not exist. So immediately you get two critical numbers, right? Negative 2 root 3 and positive 2 root 3. Okay. And all you need to do is you need to figure out when this derivative is 0, right? So notice this guy is 0 if 3 times x squared minus 4 is 0, because all of them are given by that plus or minus. Okay. So step 2. Find the critical numbers. Numbers of f. Okay, so it is coming from two different things, right? One is f prime of x equals to 0. So you set that equal to 0, and this guy is what? This is 0 if 3 times x squared minus 4 equals to 0, right? And we can divide both sides by 3. That gives x squared minus 4 equals to 0. That means x squared equals to 4. That means x equals to negative 2 and positive 2. Okay. But also f prime of x does not exist if x equals to negative 2 root 3 and positive 2 root 3. Okay. Also does not exist if x equals to negative 2 root 3 and positive 2 root 3. Okay. Therefore, the critical numbers are critical numbers of f are this: x equals to negative 2 root 3 and then negative 2 and then positive 2 and then 2 root 3. Okay? And that's the step 2. And in the third step, we're going to do that increasing decreasing fact of a function. Now we need to figure out when is this function increasing or decreasing. In fact, strictly increasing or strictly decreasing. Okay, so that's a step 3. Find the intervals on which f is strictly increasing or strictly decreasing. Okay, and from the second proposition from yesterday, this thing means i.e. find the intervals on which oh god, I need this part. What should I do? I'll keep it. Okay. Maybe I'll write it again. I.e. f prime is strictly positive or strictly negative. That's what we are going to do now. Okay, so first of all, where is f prime 0 or does not exist, you need to write that thing. So this is negative 2 root 3, and let's say this is negative 2, and this is 0, let's say this is 2, and this is 2 square root of 3. Okay, so notice at these points, say negative 2 root 3 and positive 2 root 3, f prime even does not exist. There is no point of asking whether it's positive or negative there, right? And same at negative 2 and 2, it is 0, right? At those 2 points, at negative 2 and positive 2. So it cannot be positive or negative. And now we have how many intervals? 1, 2, 3, 4, and 5. Okay, so now we have 5 intervals. And from our discussion from last time, this f prime, that's also continuous in those intervals, and so by intermediate value theorem, it's either always positive or always negative. Okay, so it suffices to check just at one point. So what we need to do is this: we need to make a table. So this is this should be a table with these things. The first column will have all the intervals. Okay, so let me just write down those intervals: negative infinity to negative 2 square root of 3, and negative 2 square root of 3 to negative 2, negative 2 up to positive 2, 2 up to 2 square root of 3, and 2 square root of 3 up to infinity. Okay, 1, 2, 3, 4, 5 intervals. You get. All right, and then from each interval we need to choose a test point. Okay. So from this interval, definitely we can choose negative 3, right? So this is negative 3. From this interval, what can I choose? Okay, I'll come back to that later. From negative 2 to 2, we can choose 0. Okay. And 2 to 2 root 3. Okay, I'll come back to that. 2 root 3 to infinity. From this interval, I can choose any number bigger than that, so I'll just choose 3. Okay. Now, can you give me a number that is between 2 and 2 square root of 3? It is 2 square root of 2, right? Yes. That's a really simple and nice number. Okay. And if this is between these two numbers, the negative of that is also between these two. So this is negative 2 square root of 2. Okay. And then we need to get a sign of this test values, sign of test values. So we don't need to get actually the values of those functions under f prime. We just need to know whether those values are positive or negative. That's what I need. Okay. And finally, from those and from our knowledge of intermediate value theorem, we need to figure out sign of f prime. Okay. All right. Now I need to rewrite this function f prime. I hope I will remember that correctly. So this is 3 times x square minus 4 if x is less than negative 2 root 3. It is d and e if x equals to negative 2 root 3. It is negative 3 times x square minus 4 if x is between negative 2 root 3 and 2 root 3. Strict inclusion here, okay, no equality. And then d and e if x equals to positive 2 root 3. And then 3 times x square minus 4 if x is bigger than 2 root 3. Okay, so this function is f prime of x. Okay. Now I need to evaluate this negative 3 where? To this function, right? F prime. Okay. Now on this interval, this function is given by f prime is given by this polynomial 3 times x square minus 4, right? So I need to plug in negative 3 here. Okay. So notice 3 is already positive, and negative 3 square minus 4 is what? 5, which is also positive. So this is positive times positive, and if you multiply to positive number, that's a positive number. Okay. So on that interval, if I plug in negative 3, I get something positive. But since my function is continuous on that interval, so it's going to be positive all in the whole interval because it does not have any zero in between. Okay, IVT. If it had a negative number, then it must have a zero in between, but there is no zero on this part of the interval. Okay, so f prime is always positive on that interval. Okay, let me write it here. Okay, so in other words, my function f is increasing on this part. Okay, now we are going to plug in negative 2 root 2. Since this is coming from this interval, so I need to plug in this negative 2 root 2 here, okay, on this interval. Notice we have negative 3, which is a negative number. And then if we plug in 2 root 2, what do we get? 2 root 2 square is 8, right? 8 minus 4 is 4, which is also positive. So this is negative times positive, which is negative, okay? And therefore, f prime is always negative on this interval. Okay, and then we are going to plug in 0, okay? And 0 is coming from this interval, right? So I will plug in here. So this is negative 3 times negative 4. So this is a product of two negative numbers, which makes it positive. Okay, so f prime is positive here. All right, now 2 root 2. So still here, right? Okay, so then this is negative, because negative 3, and then 2 root 2 square is 8, right? 8 minus 4 is 4, which is also positive. So negative times positive is also negative. So this is negative there, okay? And finally 3. So 3 is coming from this interval, right? So we need to plug in here. This guy 3, that's positive. 3 square is 9. 9 minus 4, that's also positive. So it's positive times positive, which is positive. Okay, so it's positive there. So, oh, I forgot to write those things here. So on this interval, this is negative. That means my function is decreasing. From negative 2 to 2, it is increasing. And from 2 to 2 root 3, this is decreasing. And then from 2 root 3 to infinity, it is also increasing. There we go. So negative 2 root 3, that was the critical number. And on the left side of that number, my function is increasing. And on the right side of that number, my function is decreasing, right? So what is it? It's the local maximum by the first derivative test, right? You can draw schematic diagram here. So this is, I will write there. Okay, I'll note right here. So I'll just draw a schematic diagram here, negative 2 root 3, negative 2, 2, positive 2 root 3, and infinity, okay? So at negative 2 root 3, we have some value. Let's say this is the value. It's not exact. I don't know what that value is, but the shape should look like this. On the left side, it is increasing, right? Okay. And after that, it should decrease. So let's make a little bit like this. So it's a local maximum. Okay. And then at negative 2, it is what? Decreasing up to negative 2, right? And after that, it is increasing. Okay, so at negative 2, it has the local minimum, and after 2, it also decreases. Okay, so this part goes like this. So at 2, you also have a local maximum, and after 2 root 3, it increases again. Okay, so then you get a local minimum. That's it. So you get 2 local max at negative 2 root 3 and 2, and you get 2 local min at negative 2 and positive 2 root 3. Okay. Therefore, the local maximums or maxima actually are this thing. So we need to evaluate actually the original function at those points. Okay. So f of negative 2 root 3, which is what? Our original function was this, x times absolute value of x squared minus 12, right? So this is negative 2 root 3 times negative 2 root 3 square is what? 2 square is 4, square root 3 square is 3, 4 times 3 is 12. So this is 12 minus 12, right? Which is 0, okay? So this 0 is a local maximum. Okay, and what? F of 2. Okay, so this is 2 times 2 squared, which is 4, minus 12 in the absolute value. So this is negative 8, but you have absolute value, right? So this is going to be 2 times 8, which is 16. Okay. And the local minimum are this. Yeah, this is a nice problem. It captures all the things. 2 types of local extrema and also 2 types of critical numbers. Okay. And the local minima are this. So first I need to plug in negative 2, f of negative 2, which is going to be negative 2 times 2 square is 4 minus absolute value of 4 minus 12, which is negative 2 times 8, which is negative 16, and f of 2 root 3, which is 2 root 3 times 2 root 3 square is 12, so 12 minus 12, which is 0. Okay. So that's the end of this question. And as I have been saying these things so many times, maybe you are bored, but actually these are the information we need to grab the function. Okay, some of the information. And to be honest, we need more information. In the next video, we're going to talk about concavity, and that's an important part. So once you know about local extrema, concavity, and then you know about asymptotes, you get a good shape of the graph. Okay. Okay, so let's say this is negative 2. So this is going to be positive 2. Okay, let's say this much is negative 2 root 3. So this much is positive 2 root 3. Okay. Now what happens, on the left side, this function is, left side of negative 2 root 3, this function is increasing, right? But notice, on that side, our x is negative, right? But absolute value is positive, so the whole function is negative actually. Okay, so it's like this. Okay? And after that, since this is a local max, right? After that, it decreases, right? And f of negative 2 is how much? Negative 16, right? So let's say this is, I need to go same amount on top and bottom. So let's say this is negative 16. So this much. Okay. So at negative 2, negative 16, so it comes like this. Okay. Notice we made that a corner because my function is not differentiable at negative 2 root 3. It's not smooth because the derivative does not exist. There is no tangent, right? But at negative 2 there is a tangent, so we need to make it kind of, you know, like this smoothie. Okay. And this function goes to 0 actually. F of 0 is 0, so this is x-intercept, right? And also y-intercept. This is y-intercept and one of the x-intercepts, okay? And at 2, this is 16, right? And that's another local max, so it goes like this. Okay? So negative 2 to 2, it is increasing, and after 2, it decreases and goes all the way up to 2 root 3, okay? And after 2 root 3, it increases again. And notice this at 2 root 3, it is also pointy. It's a corner because my function f, this is function f. It's not differentiable at 2 root 3 and negative 2 root 3. Okay? So that's kind of the sketch of the function. This is called curve sketching. Okay. All right. I hope it makes sense. So I'm going to the next problem now. Okay? The next problem is this: f of x equals to x times x minus 8 raised to the power 1/3. And we are going to find its local maxima and local minima. Once we find that, then we'll be done. Okay, so solution. Step 1. Since I wrote those steps in detail last time, I'm not going to do that, okay? So just find f prime of x. So f prime of x is going to be what? This is, what rule should you apply here? You have product of two things, right? A product rule, okay? So this is, first we differentiate x, which is 1, so x minus 8 raised to the power 1/3 plus, now we keep our x fixed, so x times, now derivative of x minus 8 raised to the power 1/3, right? Which rule? Power rule. So this is 1/3 x minus 8 raised to the power 1/3 minus 1, which is negative 2/3, and times, by the chain rule you have to differentiate x minus 8, but that is just 1, so not a big deal. Now this guy is what? X minus 8 to the power 1/3, it remains the same. And the next guy is, since this is a negative exponent, I will write that in the denominator, okay? So this is x on top and 3 times x minus 8 raised to the power 2/3 at the bottom, okay? Now we need to figure out its critical numbers. These are the numbers where derivative is either 0 or does not exist, right? You can immediately say where it does not exist, but you need to do something to find where it vanishes, right? So we will add those two fractions, okay? And that will give 3 times x minus 8 to the power 1/3. Oh no, is it 2/3? Yeah, it's 2/3, sorry. 2/3 at the bottom, okay? And on top, what should I get? I get 3 times x minus 8 to the power 1/3 times to the power 2 x minus 8 to the power 2/3, right? And when you multiply two powers with the same base, what do? You add the exponents, and 1/3 plus 2/3 is just 3/3, which is 1, right? So this is just 3 times x minus 8, okay? And we have plus x, plus x from the next term, okay? Let's simplify this a little bit. So if I distribute this is going to be 3x minus 24 plus x over 3 times x minus 8 raised to the power 2/3. So this is 4x minus 24 over 3 times x minus 8 to the power 2/3. Okay. All right, I will just do one more thing. I will factor out 4 from here. So I factor out 4, then this is 4 times x minus 6 on top, and at the bottom 3 times x minus 8 raised to the power 2/3. Okay. So that's step 1. Now what's step 2? Find the critical numbers. Step 2. So for critical numbers, first of all, you set your derivative equal to 0. And notice this is a fraction, right? A fraction is 0 only if the numerator is 0. So this means 4 times x minus 6 is 0, but that happens when x minus 6 equals to 0, which means x equals to 6. Okay? And what do you need? F prime of x dne. When does this derivative fail to exist? When denominator vanishes, right? dne means this x minus 8 to the power 2/3 is 0, right? But that you can actually take 3/2 power on both sides. That will just give you x minus 8 equal to 0, and that will give x equals to 8. Okay? But careful, is 8 in the domain of this function? Yes, it is. Right? This function f has everything in its domain, because this is cube root, and cube root is defined everywhere. Okay, so these are my critical numbers, right? Then what is the next step? Step 3, find the intervals where it's increasing or decreasing, right? And here I have just 2 points, 6 and 8. These are two critical numbers. So intervals, we'll have 3 intervals, negative infinity to 6. Is it too congested? Maybe I'll write it over there. Okay. Actually, I should have write those things here. Step 3. Okay. First, draw a number line and then plot those critical numbers. 6 and 8. Notice at 6, first derivative is 0, so it cannot be either positive or negative, and at 8 it even does not exist. Okay, but otherwise it is always either positive or always negative. Okay, so then intervals and test points. I'm going to, and then sign. I'm going to drop one more, the third column from here. You can write it, but I don't have enough space. Okay, so negative infinity to 6. What point I can plug in? 5. Okay. And then 6 to 8. Definitely the easiest point is going to be 7. And then 8 to infinity, we'll plug in 9. Okay. and then we are going to plug in. So yeah, I told you this, but I never emphasize this thing. Don't forget this thing. You need to plug in these values to the derivative, not to the original function. When you are checking increasing decreasing property of a function, you plug in those things in the derivative. Okay, and once you know where you have the local maximum and local minimum, you evaluate the original function, not the derivative. Okay, yeah, this happens all the time. So we plug in 5 here. Okay, so on top I have what? 4 times 5 minus 6, right? Which is 4 times negative 1. So on top I have something negative, right? But what happens at the bottom? Notice in the bottom I have this. Let me write it here. Prime of x is 4 times x minus 6, and this is 3 times power 2/3, means first you take the cube root and then you square. So this thing is x minus 8 raised to the power 1/3 and then you square. Okay. Now notice this is after all a square, so it's always going to be positive. It times 3, it's still positive, right? So whether my f prime is positive or negative, it completely depends on what? This x minus 6, right? Okay, so if I plug in 5, then this is 5 minus 6 negative 1, so it's negative. If I plug in 7, then 7 minus 6 is positive 1, so it's positive. Okay, and then if I plug in 9, then 9 minus 6 is 3, which is also positive. Okay, all right. So let's just put these signs over here. So on this interval it's decreasing, on this interval it's increasing, and on that interval it is also increasing. Okay, another nice fact. Do you remember the first derivative test? The third condition is what? If it is increasing to increasing, or if it is decreasing to decreasing, then it's neither local max nor local min, right? So notice it's increasing to increasing, right? So x equal to 8 will not be a local extrema. Okay, so we are ready to write down the extrema. Therefore the only local extrema is f of 6, right? What was the function? One more time. The function was x times x minus 8 raised to the power 1/3. Okay, so f of 6 is going to be 6 times 6 minus 8, which is negative 2 to the power 1/3. Okay, all right, and cube root of negative 2 is negative times cube root of 2, which is negative 6 times cube root of 2. Okay, which is it local max or min? It decreases and then increases, right? So it's a local minimum. Is a local minimum. So this function does not have a local maximum. Okay, so that's the end of finding local extrema. And once again, let me just sketch this function a little bit, okay, to give you a feeling why we care about those extrema and other things which will show up in few days. Okay, so x-axis, y-axis. Okay. Oh, by the way, I always forget this function. This is x times x minus 8 to the power 1/3. So at 0, this is definitely 0. Okay, that's not so important. What happens at 6? At 6 we have, let's say this is 6. how do you do 2, 4, 6, 8. Okay, so this is 6, and negative 6 2 root 3 is somewhere here. This is negative 6 cube root 3. Okay, so this is a local minimum, and here is 8, right? And something interesting happens at 8. That's why I like this problem. Anyway, notice one thing: if x is negative, then this guy is negative, that guy is also negative. But negative times negative is positive, right? And if x goes to negative infinity, that guy goes to positive infinity. So the graph kind of looks like this. Although I don't know the exact graph, we need more information to get the exact graph. But does it look like this? Or does it look like that? Yeah. So actually this is a very good point to advertise the next topic. The next topic is concavity, and that actually will tell us whether this looks like this or it looks like that. Okay, I need to calculate the second derivative, but I don't know anything right now, so let's take a guess. Okay, after all, I'm not a sketching graph here, so I'm just showing you what possible things we can get. Okay, so here, and then this is a local minimum, right? And what happens at 8? If you plug in 8, it is 0, right? It's another x-intercept. So it goes up to here. But there is one important thing. Oh God, I also erase f prime of x. But notice f prime of x does not exist at 8, right? Because as you are approaching to 8, you see you have x minus 8 at the bottom. And then there is a squared, right? So if you are approaching 8 there, f prime of x goes to infinity. So what does it mean? Slope is going towards infinity. That means it's a vertical tangent, right? Okay, so at x equals to 8, oh God. All right, I will call this guy 8. Okay, so it's a vertical tangent, so it almost looks like this in this part, and after that it goes to infinity. So after that it goes like this. So it's kind of like this shape. Okay, actually, yeah, I realized 6 is here. Okay, so the point, the graph should be more like this. Like this, almost like that. Okay, so that's a sketch of this function f. Anyway, so you see from here we need actually more information, and what we need is the behavior of the second derivative of a function, and that relates to a geometric fact which is called concavity or convexity. Okay, and that will give us a better idea of the shape of the graph. Okay, and that's what we are going to do next time. And I hope this makes sense, and I hope you have enjoyed this long episodes of Extrema. It's long, but it's not too bad. But anyway, see you next time.